So in this video, I'm going to do some examples of finding the prime factorization of a number. When I'm finding the prime factorization of a number, my goal is to find all of the prime numbers that you have to multiply together to get my target number. One advantage of doing a prime factorization compared to all of the other possible ways that we can factor numbers is that the prime factorization is unique. So there will only be one prime factorization. There's only one way to factor a number into prime numbers. So the next question is, how do we figure out what the prime factorization is? And to do that, the divisibility test for 2, 3, and 5 will be really handy. So a number is divisible by 2, which is a prime number, if it's an even number. So that is if it ends in a 0, a 2, a 4, a 6, or an 8. A number is divisible by 3 if the sum of its digits is also divisible by 3. I know this one's a little bit weird. So what you'll do is you'll add up all of the digits of your target number, and if you get something that is divisible by 3, like 3 or 6 or 9 or 12, then the original number was also divisible by 3. Here's an example to help make sense of that. 81 is divisible by 3 because 8 plus 1 is 9, and 9 is divisible by 3. Finally, a number is divisible by 5 if it ends with a 0 or a 5, like 25 or 100 or 70 or 75. All of those are divisible by 5. I think it must be time for an example. Let's find the prime factorization of 36. In this example, I'm going to do this in several different ways so that we can see that we always get the same answer no matter how you choose to start factoring. First, I'm going to look at the 36 and notice that it's even. So I'm going to factor out a 2. That leaves me with an 18. 18 is also even, so I can factor out 2 again, leaving me with 9, which factors into 3 and 3. Now the branches of my factor tree are all prime numbers, so I'm done. And I know that the prime factorization of 36 is 2 times 2 times 3 times 3, or 2 2's and 2 3's. This time, I'm going to use the fact that 36 factors into 4 and 9, which I might know from my 4 times table or my 9 times table. Then I'll factor 4 into 2 and 2 and 9 into 3 and 3. Notice that once again, we got 2 2's and 2 3's. This time, I'm going to factor 36 into 6 and 6. Again, I might know that from my 6 times table. Each 6 factors into a 2 and a 3, so again, I get 2 2's and 2 3's. So no matter how we get there, we end up with the prime factorization of 36 being 2 times 2 times 3 times 3. Now let's go ahead and find the prime factorization of 105. So here is 105, and I'm going to start through my list of small prime numbers, seeing which ones will go into this number. So this number is not even, so 2 won't go into it. So I can't try that one. It is obviously divisible by 5 because the last digit is a 5, so I might choose to use 5. It also turns out that this number is divisible by 3. I can use the divisibility by 3 test. If I add up all of the digits, 1 plus 0 plus 5 is 6. And 6 is divisible by 3, so I know that I'm going to get a 3 in here eventually. I like 5 since that's one that I can do the division with pretty easily, so here's 105. I'm going to divide it by 5 and see what I get. 5 goes into 1 0 times, into 10 twice, and into 5 once, so there's a 21. 5 and 21. Now I look at this number 21. I happen to know that 21 is 7 times 3, so I can pull this down to be 3 and 7. Both 3 and 7 are prime numbers. So I've found my prime factorization. 105 is the same as 5 times 3 times 7. I guess we usually write those in order from smallest to largest, but it really doesn't matter. You can write it either way here. Here's another example. This time we're going to find the prime factorization of 243. So again, I'm going to make a factor tree. I start with my number 243, and I have to start deciding what numbers might go into it. So I have sort of a mental list of sort of small prime numbers. So I'm going to start by thinking of the number 2, since that's my smallest prime number, but this number is not even, so 2 is not going to go into it. 3 is the next prime number. I can use the divisibility test for 3 to see if this is divisible by 3. To do that, I add up all the digits and see if that number is divisible by 3. I know it's kind of a weird test, but it works, which is cool. So 1, 2, 3, 4, 5, 6, 7, 8, 9. When I add up all the digits, I get 9. 9 is divisible by 3, which means that this number must also be divisible by 3. Okay, so I'm going to go ahead and pull a 3 out of this number. I need to do this over here by hand. I can't actually quite do it in my head. 3 doesn't go into 2, but it does go into 24 8 times, right? And then it goes into 3 1 time. So I've got a 3 and an 81. Now from here, I can go through the same test. I can see 2 won't go into 81, 3 will, but you know, I happen to know that 81 is 9 times 9. And I like breaking this down as soon as I can into smaller numbers that I recognize. So I'm going to break this down into 9 and 9. Now, each of these 9s, they're not prime, but each 9 is 3 times 3, and 3 is prime. So now I've gotten all of the ends of my factor tree are prime numbers, so I can count up what I've got left. 1, 2, 3, 4, 5. Looks like all I ended up with was 3s. So I can say 243 is 3 times 3 times 3 times 3 times 3, or I might say that it is 3 to the 5th. Either one of those would be fine. Okay, so here's one more example. We're going to find the prime factorization of 140. So I start with 140 at the top of my factor tree. I'm looking to split this into two things that multiply together to be 140. Really, any two things will do. I happen to notice that this number is even, so I'm going to start by pulling out a 2. I especially like 2 because it's usually division that I can do in my head. So 140 divided by 2 leaves me with 70. Then that 2 is prime, so don't have to worry about that one anymore. Now I need to factor the 70 since it's not prime. I could use 2 again, since 70 is an even number. I could pull out a 2. 70 also ends with a 0, so I could pull out a 5, since I know that all numbers that end in 0 or 5 are divisible by 5. But I kind of like making this 7 times 10. 7 times 10 is 70. And then that 7 is prime, so I don't have to worry about that one anymore. 10 is the same as 2 times 5, and both of those are prime. So looks like I'm all set. I've got prime, 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 prime. All the ends of my factor tree are prime numbers. So I can say that 140 is 2 times 7 times 2 times 5. Now, technically this is correct, but this is probably not how you'll see it written in the back of the book. We usually group the numbers that are the same together. So I'm going to write this as 2 squared, and then we usually write them from smallest to largest, but it's not really a big deal. So 2 squared times 5 times 7 means exactly the same thing as what we have written there.